All right, guys. Mr. Jenkins here with lesson 6.2, which is about multiplying radical expressions. All right, so that's what we're doing. So to begin, there's a lot of simplifying radical expressions here. Remember, we did a lot of that in some previous chapter work, also a DMR over it. And remember, when we do that, we're trying to, take out the biggest perfect square. So in this case, we would break down 200 into the square root of 100 times the square root of 2, which gives us 10 square roots of 2. Okay, and then 75 would be 25 times 3. So square root of 25 is 5. And square root of 3 is just square root of 3. Okay, and just kind of an important fundamental note, and I know I've gone over this before, but if you're ever not sure, a couple things you need to check about your final answer. One, is there any perfect square that goes into what's under the radical? 2 is 10 square roots of 2 really equivalent to the square root of 200? You can kind of just quickly check that. Type it into your calculator. All right, so second square root, and then so the square root of 200 is equivalent to, we see the decimal between 14 and 15, and then 10 square roots of 2, which means 10 times the square root of 2 is equal to the exact same decimal. Okay, so that's a good way to kind of check. All right, so the next one, the next set of examples says, if the radicand has a perfect root among its factors, you can use the product rule to simplify. This is called simplest radical form and is not a calculator estimate, right? So kind of what we just went over there. All right, so now since we've done it with square roots, now we're going to do it with higher roots. Okay, so we don't know. We know our perfect squares pretty well, but we don't really know our perfect cubes as well, right? So I suggest listing them out. All right, so like our perfect cubes would be, all right, 1 cubed, which we don't really care about 1 cubed, but that's 1. 2 cubed is 8. 3 cubed is 27, right? And these are the numbers you need to keep dividing by. 4 cubed is 64. None of these numbers divide into 250. Well, 8 might, I'm not sure. No, I don't think it does. And then 5 cubed is 125. So we can tell 125 divides into that, but sometimes you have to just keep going that way. But we would break this down into the cube root of 125. There's our perfect cube times cube root of 2, because 125 times 2 is 250, or 250 divided by 125 is 2. Think about that either way. So then the cube root of that is 5. So this is equal to 5 cube roots of 2. Now you can just write it like that. I kind of suggest putting a dot in between them just because that can look like 53 square roots of 2. So just for neatness purposes, if you ever had to handwrite it, a dot is nice. If you're typing on a computer, which a lot of times you will be this year, then just the 5 cube roots of 2 would work. All right, looking at the next one, the 5th root of 160, right? So now we're thinking fifth roots are going to be, or 5th powers are going to be really big. So let's think about our perfect, whatever you would call that. So 1 to the 5th power is 1. We never care about that one, but I'll list it anyways. 2 to the 5th power is 32. So let's see if 32 goes into 160. I believe that it does. So there you go. All right, and then you could keep going, but we don't need to at that point. We see we found our perfect 5th root. All right, so we break this down into the 5th root of 32 times the 5th root of 5. And so simplifies to 2 times the 5th root of 5. So the logic is exactly the same as if you are doing simplest radical form with a square root. I'll leave C and D for you to try. So the 4th root of 162, the 3rd root of 56. Looking at the next one, now we're going to deal with some expressions that look like some of yesterday's, and I got into this on yesterday's notes, and you know, it turns out I didn't really need to. I forgot that it was in this lesson, so could have just waited. But remember that when we take the root of a power, we divide the exponent. That's my exponent rule here. So step 1 is to kind of know that. So here we have a to the 3 over 3 times b to the 8 over 3. All right, so then we think about, 3 going into 8. It goes in twice with 2 left over, okay? So here's how that shows up in our final answer. Obviously, 3 over 3 is 1, so a to the 3rd is a perfect cube, so that's just outside the radical. And then we can take a b squared out of there, so b squared, that's this 2, goes there. And then we also have something left under the radical, so the cube root of whatever's left, so that would be b squared, because we have that remainder of 2. Okay, so hopefully that makes sense. Then we wouldn't care about the even, odd rule because we're taking an odd root there, or my index is odd. You could say that either way. So a times b squared times the cube root of b squared would be our final answer there. Let's do one more of those because those can be tricky. So next one, we have the square root of x to the 7, y to the 9, z to the 1. All right, so remember my index here is 2 if nothing's written there. So we have x to the 7 over 2 times y to the 9 over 2 times z to the 1 over 2. All right, so what comes outside, I think about that first. So 2 goes into 7 3 times, so we have an x to the 3 outside the radical. We have a y to the, how many 2's into 9? That'd be 4. How many 2's into 1? That'd be 0. So no power of z comes out from under the radical. So we have x to the 3 times y to the 4 times the square root of whatever's left. So we have an x to the 1, a y to the 1, and a z to the 1 underneath. Those are my remainders. Okay. Now the next question would be, why did I not talk about the even, odd rule here? Because we took an even root and we ended up with an odd power. So what prevented me from needing to put the absolute value bars here? That's the question. Okay, I know that even, odd rule can be tricky. All right, so moving on. Doing some more examples. Now we get into the kind of, I guess, more of the meat and potatoes of the lesson where we have to multiply. All right, so you kind of multiply first and then you worry about simplifying at the end. So this is equal to the square root of the product of 2 times 6. So the square root of 12. And then at the end, you want to make sure it's in simplest radical form. Right, so is there any perfect square that goes into 12? Yes, 4, right? So the square root of 4 is 2. And 12 divided by 4 is 3. So 2 square roots of 3. Looking at the next one, obviously we have a higher root here, so that's going to be a little tougher. And again, I suggest multiplying first. So keep all this straight in your head. When we multiply, our exponent rule is that we add the exponents. So after we multiply here, we end up with the fourth root of x to the 2 plus 5 is x to the 7. And then y to the 3 plus 1 is y to the 4. All right, so then we go ahead and, sorry, I just realized I skipped a part up there. I'll look at that here in just a sec. So then we end up with, when we simplify, 7 over 4 would be 1, so we have an x coming out. And then 4 over 4 would be 1, so we have a y to the 1 coming out. And then we're left with, what are we left with? So we have the times the fourth root of, so we'd have a remainder of 3 for this one, so x to the 3. And then we took, this has no remainder, so that stays. All right, so x times y times the fourth root of x cubed. Now, the even, odd rule will apply on this one, right? So the answer to that last question was, just to review, the even, odd rule did not apply here because this would be even, and then that's odd. So that would be even, odd, odd, right? So not even, odd. Here, though, okay, when we think about simplifying, that's where you think about it from. We had even, and then 1 is odd, right? So we do need those absolute value bars around the y. So x times the absolute value of y times the fourth root of x cubed. So you see how these can get a little bit complicated. So let me go back over what I skipped there. All right, so can you simplify these? The answer here would be no, you wouldn't multiply these because those are different roots. The answer here would be yes, because we have the same root, so this would be equal to the fifth root of 10. All right, so definitely should have done that first, but okay, so I will leave C for you to look at, and let's look at maybe D and then maybe one more. All right, so again, you want to kind of treat this stuff like terms, all right? So the stuff outside the radical, we multiply together. So the 4 times 3, treat that like a coefficient. And then we have the square root of 2x times the square root of 8x. So that would be multiplied by, the square root of 2x times 8x. And I'm showing a little bit more work than maybe I need to, but that's okay. So anyways, after I multiply, what I get is 12 square roots of 16x squared. All right, and what's under my radical is actually a perfect square in this case. So we have 12 times the square root of 16 is 4. And then the square root of x squared is x. So this would be, looks like an even, odd rule is going to apply here. And then we just simplify. So 12 times 4 is 48. And then don't forget your even, odd rule. So 48 times the absolute value of x. Okay, and then let's do one more where we have those kind of coefficients out front. So I'll leave G for you and try H. Okay, so again, 7 times 2 is going to give me 14. Then we have the square root of 3 times 6 is going to be 18. Let me let that screen catch up real quick so I'm not writing all over the place. So 3 times 6, 18. X cubed stays x cubed, and then y to the 2 plus 1 is y to the 3. Thinking about breaking this down. 9 goes into 18. That's a perfect square. So let me just show this work a little bit different way. Here's maybe another way you could show your work. So we have 14 times. Let me just break it all the way down. So times the square root of 9 times the square root of 2. And then x cubed could be broken down. I don't know if you want to show your work this way or not. Times the square root of x squared times the square root of x. And then y cubed, square root of y squared times square root of y. This is just kind of maybe a different way to think about it, right? So then as we start to simplify, we have 14 times 3 times x times y. And then whatever's left under the radical. So my non-perfect squares were square root of 2, square root of x, square root of y. So square root of 2xy. So final simplified answer, 14 times 3 is 42. So we have 42xy times the square root of 2xy. Okay, and then let's think real quick. Even odd rule doesn't apply because we had an even root, but both of those were odd. Okay. All right, so moving on, there are a couple more up there that I skipped that you can try on your own. All right, so our last thing, last year I made this a 2-day lesson, but I'll go ahead and throw it all in this one video for you today because tomorrow, Friday, we will do a Q&A over this, so that's why I'll make this a bigger lesson than maybe normal. All right, so we're going to look at what happens when you divide by a radical. And the answer is that we have to, okay, so I'm getting a little bit ahead of myself. Well, these would be easy examples here, okay? So, just like if we took 18x to the 5 times 2x times the square root of 2x to the 3, we'd multiply and put under the radical. Here we can divide, right? So in other words, this is equivalent to the square root of 18x to the 5 divided by, sorry, that doesn't look pretty, 2x to the 3, right? So basically, like a DMR problem, I would do 18 over 2 is 9. So square root of 9. And then x to the 5 over x to the 3 would be x to the 2. And then we would just simplify from there, right? So we get square root of 9 is 3. Square root of x squared is x to the 1. And it looks like the even, odd rule applies there. So we would want to put the absolute value bars around the x. So 3 times the absolute value of x. Let's maybe do one more there that doesn't work out as pretty. Maybe a higher root. All right, so let's go ahead and do that. So 162 over 3, that part is equivalent to, 54. Then x to the 5 over y to the 2. Let's change that to x squared. I think I meant to do that on the notes. We're not going to get into a different variable right now. So we'll just change that to x squared. So x to the 5 over x to the 2 is what we're going to pretend that says would be x to the 3. And then we try to simplify. So is 54 a perfect cube? I don't know about you guys, but I have to list these out. 1 cubed is 1. 2 cubed is 8. 8 doesn't go into 54. 3 cubed, I think that's going to be our winner, is 27. And then the next one's bigger than 54. So our breakdown would be, so the cube root of 27 is going to be 3. All right, so I'll skip a little bit of work here. So we have 3 outside the radical, and then the cube root of x cubed is just x. And then what would be left under, you know, so 27 times 2 is 54. So just the cube root of 2. 3x cube roots of 2 would be our answer there. All right, now let's get to your toughest type of question. And this is where this could be a 2-day lesson. But if it says rationalize the denominator, we've done stuff similar to this. So we talked about, like, you know, when we're dealing with imaginary numbers, you treat irrational numbers a lot like imaginary numbers. But basically, an imaginary number couldn't have an imaginary number in the denominator. Same thing here. You can't have an irrational number under the radical. Okay, so how do we deal with that? And if we have 4, I'll probably do maybe 3 of these. Leave 1 for you. All right, so let's just get right to it. So you always have to think about the root here. We're taking the second root, okay, and we're worried about the denominator. All right, so what can I do to 6 to make it a perfect square? And I say square because we're taking the second root. And the easy answer to that is to multiply it by 6, right? So that tells me we need to multiply by the square root of 6 over the square root of 6. And so when we do that, what we get on the denominator is the square root of 36, which is 6, right? And then we get whatever we get on top. So the square root of x times the square root of x is just the square root of 6x, which can't be simplified. No perfect square goes into either one of those. So that would be my final answer. Okay. Now let's look at a cube. Okay. All right. So in this case, first thing we need to understand is that this is equivalent to the cube root of 9x divided by the cube root, hopefully this shows up right, of 2. Okay, so then how can I make a perfect cube, right? So you're thinking you want 2 to the 3rd power, right? Goodness gracious, falling apart here. Give me just a second. All right, we'll try that again. All right, I'm gonna cut this out of the video. Okay, so yeah, we want 2 to the 3rd power. Okay, so 2 times what would be equal to 2 to the 3rd power? That'd be 2 times 2 to the 2nd power, right? Because you have 2 to the 1 times 2 to the 2 would be 2 to the 3. Hopefully that makes sense. That's kind of the key to these. So multiplying by the cube root of, I'm going to write 2 squared. You could write 4 there because that means the same thing. But I'll write 4 up top just because that's the more normal way to write that. All right, so what we end up with is on the bottom, the cube root of 2 cubed, or the cube root of 8, which would be 2, okay? So we have something over 2. So now we just multiply. 9 times 4 is 36. So up top, we have the cube root of 36x. And then you always want to make sure that you're fully simplified at the end. So thinking about our perfect cubes besides 1, 8 doesn't go into 36, 27 doesn't go into 36, and then 64 doesn't go into 36. So at that point, you know you are finished. All right, so let's maybe look at just one more, and then I'll leave a last one for you. Okay, so let me do. C. Okay, so square root. So we're thinking perfect square. So there are a couple things you could do there. You could just square that, so you could multiply by another square root of 2y cubed. Or you could be a little more efficient and think, all I really need to add to that is a 1. So I could just multiply by the square root of 2y, if that makes sense. If you forget that though, just square that number. But I'm going to be just a little bit more efficient on this one. And so what I end up with there, I'll just show an extra step, is for my denominator, the square root of 4y to the 4, which is a perfect square. So I'm good. Under 18 times 2 is 36. So the square root of 36, x squared, and then y to the 1 times y to the 1 is y to the 2. All right, so now we just simplify, and then we should be done. All right, so this up top appears to be a perfect square. So the square root of 36 is 6. The square root of x squared is x. The square root of y squared is y. That's my numerator, and then my denominator is, let's see, the square root of 4x to the 4, so that'd be 2x squared. Sorry, that's a y. Wondering why that wasn't working out right. Over, and that's 4y to the 4th. Sorry about my handwriting there. So that would be 2 times y squared. 2y squared. All right, so then we just want to simplify. Also thinking about the even, odd rule is going to apply up top. Well, let's go ahead and simplify this first. 6 over 2 gives me 3. And then we have x up top. And then we'd have y to the 1 minus 2, right? So that'd be y to the negative 1. So all of that would be over y. 3x over y. And again, that even, odd rule does apply here. Even, odd. All right, so 3 times the square root of x over y. Okay, so those can be difficult. I'm sure you'll have questions, but we'll have a Q&A day on Friday, so let me know what you guys need help with. Hope this helps. You guys have a great one.